Okay, so today we are going to talk about section 4 in chapter 24, inductors and AC circuits. This is the case that we have AC circuits that contain only inductors. Now we will see that the behavior of inductors is in many aspects just the opposite of that the capacitors. This figure here, which is same as your figure 2415 in your book, shows the voltage, which is the voltage of the AC generator that is connected to an inductor. If you remember, for the case of capacitor, the voltage across the capacitor was equal to I times X sub C, and this X sub C was called the capacitive reactance. Now, the reactance for capacitor was equal to 1 over omega C, and this is just a small note here. In case of the inductor, I can define voltage across the inductor to be I times X sub L. Now, this XL here is the inductive reactance, and it is equal to omega times L. Now, omega is the angular frequency and L is the inductance. Alright, so again, because this is a type of the resistor in the circuit, the unit is ohms. Like the previous cases, if I want to find the current in such a circuit, I start with the general Ohm's law, or the common form of Ohm's law, and then I find I to be V divided by R. In the case that I have the reactance, that would be I RMS equals to V RMS divided by XC. Now if I have the inductor, then the value RMS of the current equals to voltage divided by XL. Now because XL is indeed omega L, this is equal to V RMS divided by omega L. Let's take a look at exercise 2412. It says a 35 millihenry inductor, and if you remember, Henry was the unit for inductance, is connected to an AC generator with an RMS voltage of 24 volts and a frequency of 60 Hertz. What is the RMS current in the inductor? Like always, I begin by writing the unknown of the problems and the known of the problems. You can see here that I organize everything. Now the equation that I'm going to use is the same equation. So let's just plug in the numbers. IRMS equals to, I have 24 volts for the RMS voltage of the circuit. And then I have, sorry, this is the mistake here, times omega L. Now omega was 2 pi F. This is what we use always. So 2 pi times 60 Hertz. And then times L, which is 35 times 10 to the power of negative 3 Henry. So I'm just converting the milli to Henry here. So if you calculate this, you will get around 1.8 amps. Alright, if I want to plot the voltage and current with respect to omega t, so if I have the current like this, which is a sinusoidal wave, so this is my current, then the voltage will reach the maximum value before the current. So with that definition, I know that this is my voltage, so this is the graph of the voltage here, and you can see that it just reaches, so okay, hold on. So this is my voltage here. So you see that it reaches the current or it reaches the maximum before the current. Okay, so the voltage and current in the circuits that only has inductor has pi/2 difference, right? So here, if you're talking about the average of power, so we follow the same equation, which is IRMS VRMS times cosine phi. This phi is the angle between voltage and current. So in this case, this is pi/2 or 90 degree, which is 0. So the average of power for the circuits that only has inductors is 0. Okay, let's talk about the phasor diagram. So like the previous cases, we need to be able to show how the current and voltage reacting to each other in terms of the phasor diagrams. So like always, I start with I max, and I choose theta to be the direction of I max on my phasor diagram. Then if I want to show the phasor for the voltage, I know that voltage reaches the maximum value before current. Or simply we say that voltage phasor leads the current phasor by 90 degree. So in the case of capacitor, voltage phasor was lagging the current by 90 degree. Here, the voltage phasor is leading the current by phase 90 degree. Okay, next let's talk some about the case that we have both resistor and inductor, and only the resistor and inductor in the system. Very similar to the case that we had RC circuits, we can have RL circuits. In RL circuits, as obvious from its name, we have a resistor and we have an inductor. Now let's figure out what is the relationship between the maximum voltage and the maximum current here. If you remember from the previous RC circuits, we defined something called impedance. For that case, impedance was square root of R squared plus XC squared. So this is just a note here to remind you. So very similar to that, the impedance in an RL circuit will be the square root of R squared plus XL squared. And if I break this into its component, it's going to give me R square root of R squared plus omega L squared. The equation for the phase difference is exactly the same. So cosine phi is R divided by Z, which is R divided by square root of R squared plus omega L squared. Okay, how about the relationship between voltage and current? Now, if you think about it, we have exactly the same thing. So V max is gonna be I max times Z, and then here is the Z that we use. And the same for RMS values. So V equals to I times Z. Okay, let's take a look at example 2413 on your book. It says a 0.38 Henry inductor and a 225 ohms resistor are connected in series to an AC generator with an RMS voltage of 30 volts. And a frequency of 60 hertz. It's really nice that the frequency is always 60 hertz because this is what we use in the United States, but be ready if like you have something else other than 60 hertz. In part A, we want to find the RMS current in the circuit. Now, it's important to know what equation we are going to use and how to organize this problem. I start with the Ohm's law. VRMS equals to IRMS times Z, and I know that because I have the resistor and the inductor here, my Z is going to be R squared plus omega L squared. Okay, so let's just solve this problem for IRMS. Because we're going to use this impedance here, it's really useful if we find a value separately. So this is going to be square root of 225 ohms squared plus omega is 2 pi f, so it's going to be 2 pi times 60 hertz times 0.38 Henry, and all this squared. So please be aware and be careful about like how you square each part separately. So with these numbers, Z is going to be 267 ohm, and again remember that this is a type of a resistor or resistance, so impedance has the unit of ohm. Now if I put the value of VRMS here, 30 volts divided by Z, which is 267 volts, my IRMS is going to be 0.112 amps. Part B is asking for the RMS voltage across the resistor. So for resistor alone, the voltage across it is going to be the current across the resistor times the resistance. Since I have found the RMS current, the general one, the total one in the circuit in part A, I can just plug in here. Now, remember that if part A was not given and they ask you for the voltage across the resistor, you should have still done part A in order to find the current in the circuit. Now let's plug in the IRMS, which is 0.112 amps times 225 ohm, and this is giving me the voltage of 25.2 volts. Okay, part C is asking about the RMS voltage across the inductor. So now I want to find VRMS across the inductor. So again, I take the total current in the circuit and multiply it by the inductive reactance, which is indeed omega L. So I'm gonna multiply for the VRMS across the inductor. I'm going to multiply 0.112 amps by 2 pi F, which is 60 hertz, times 0.38 Henry. Okay, it seems that I don't have enough space to write the answer here, so I'm going to write it on the other side. It's going to be 16 volts. And now that we know the relationship between the impedance and every part of the circuit for the RL circuits, it's important that we know how to draw the phasor diagram. So like usual, we start with drawing the Imax for the circuit. This is Imax, and this is the figure 2420 in your book. Okay, so we know that if Imax is in this direction, then the resistance, the current in the resistance and the voltage in the resistance is going to point in the same direction. So this is the first section that we studied. So this will be Imax times R, and then we know that this is moving with angular frequency omega. When it comes to inductor, we know that it is going to be 90-degree difference between the voltage across the inductor. So this is the voltage across the inductor, which is Imax times XL. So let's call this Vmax across the inductor. Okay, so now we are dealing with two phasors here. The one that is for the resistor, and we're talking about voltage, and the one that is for the inductor. Okay, my figure here is not as beautiful as your book, but if we do the vector summation, then this vector here is the total of the voltage, which is Imax times Z. So this is the total Vmax. And then the angle that this total vector makes with the Imax was called phi. So this is the impedance that we were talking here. So this phasor here, which is I max Z, shows the voltage for the R, or the total voltage across the RL circuit, and then again Z is R squared plus XL squared. And that is kind of obvious from this picture, because this is the same as the vector summation between the I max R and then I max XL vectors. Now this brings us to the end of this section. We'll shortly start section 24.5. And again, like always, please let me know if you have any questions. I made a quiz number 4 for you online. It will be open tonight at 11:59 p.m. and you are going to have time till Monday 11:59 p.m. But the limit for taking the quiz is 30 minutes. Now, I provided all the descriptions and instructions for taking that quiz, but because that is from every topic in this chapter, so please be patient and first watch the videos and then take the quiz, because it's going to be only one attempt and one shot. Well, stay healthy and stay safe.